Everybody, the goal of this video is to help you understand these definitions for oscillations. I'm also going to show you a demonstration. Give me just a second. And hopefully that will help you relate these terms to some of the workbook problems that we're going to be doing as we learn about oscillations. We're not going to be talking about pendulums yet, but when we do, a lot of these terms will apply. So let's get right to it. Let me first start by showing you the apparatus that we're talking about here. Whoops, wrong one, 8. There we go. Let me zoom in just a little bit. Let me tilt up. Okay, so we have some mass springs here. And the idea is, here's the spring, here's the spring. You can see there's many different types of springs. I'm going to bring 2 more over here. The classic spring that you always see in a physics textbook is one that can be compressed or stretched. So when we look at this one right here, this one, as you can see, I can't really compress this one. I can only stretch it. But this one over here is the one that I want to work with. You'll see that you can actually compress. You can actually compress this a little bit if you need to. All right, so give me a second. Auspicious beginnings, huh? Oh my goodness. Just using this. Okay, so you can see that you can compress this if we need to. All right, and what mass was on there? I think this one was on here. We can see that thing oscillating. I'm going to throw a mass on here. We can watch this one oscillate. And one of the things you hopefully notice is that this oscillation appears to be a little bit faster than that one. And so what factors affect that? Gee, it's probably the strength of the spring and the size of the mass. So that's one of the things that we're going to get into. And in particular, I'll show you that if we apply less mass, you might think to yourself, if I apply less mass to this spring, will it oscillate faster or slower? If you want to pause the video, you can. I'm going to go ahead and run this right now. We see it bouncing. I'm going to record the period. Let me see if I can do this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I got about 0.45 seconds. I'm going to round that to 4 seconds. So it looks like it took about 4 seconds for this spring to oscillate 10 times. So the period is 0.4 seconds. Let's go back to the board and talk about this. Get over here. All right. So let's start with this. This period is the time for one oscillation. Now, as I just mentioned, we saw this thing bounce up and down about 10 times in 4 seconds. So I'm going to say the period, and I'm going to use this symbol for the period, this double T, is equal to 0.4 seconds. All right. Maybe it's closer to 0.45, but there could be some reaction time. We saw it starting to swing around a little bit, but that's what the period means. Let's go right into the frequency. That's the symbol F. That's cycles per second. It's also equal to 1 over the period, which in this case, this would be 1 over 0.4. What is that? 0.4 is 4/10, so that's 10 over 4. What is that? 2.5 hertz is the unit. Okay, sometimes you'll see that as 2.5 seconds to the -1. I like to remember that hertz kind of sounds like the German word for heart, which beats about once per second. So if that helps you remember that, great. If it doesn't, who cares? So the units of frequency are hertz. The units of period are seconds, and they're related. Angular frequency, if you remember from your introductory physics class, that's omega, not W, okay? This is a W, pointy. Omega is curvy, all right? Let's just write the word omega. So try to call that omega. Everybody screws up, but whatever. Try to get in that habit of calling it omega. And that's just 2 pi f which is basically converting this to radians per second. Whoops, let's go ahead and do the math real quick. Did I bring a calculator? Oh my gosh, did I forget? Please be here. Okay, on here. So 2 times pi times, what was it? 2.5. I got 15.7. Now I'm being a little bit loose here with sig figs. This one has about 1, so this should only have 1. So this one should only have 1. Exception, first digit is a 1, add a sig fig. But that's fine. Maybe what I'll do is I'll just round off and say this is 0.40, even though there's some error in this number, all right? So there's some rounding error. You may see this in the book where I underline things to indicate where the rounding digit is. And we sometimes keep an extra digit when the first digit is a 1. So now those all are indicated as 2 sig fig numbers, all right? Spring constant, just a quick reminder on that. K is the spring constant, all right? And in units of newtons per meter. It turns out we're going to be doing oscillations in this chapter and use the letter K for spring constant with these units. In the next chapter, we're going to be talking about waves. K will mean something else. It will have different units. So it's going to be important to really pay attention to the units on these parameters, not just the symbol used, because sometimes the symbol K will have these units. Sometimes the symbol K will have a totally different meaning in the next chapter. Similarly, that's why I'm writing period this way with this kind of funky looking T, because we've got time, we've got tension, we've got torque. There's a lot of different letter T's that we could be using. So I'm going to use this double T, double T for the pendulum. All right, now amplitude and Y equilibrium. So let's look here at this picture really quick. We saw that when I first put the mass on the spring, it was unstretched. And then it's bouncing around. You could imagine that if you leave it long enough, in fact, I'll even pop over there real quick. You can see that this one's starting to come to equilibrium right here. This one's still going, but this one's kind of reached equilibrium right about there. So going back to the whiteboard, we see that if it stops oscillating and it reaches equilibrium, we know that the force up, hopefully this green will show up. The force from the spring upwards balances mg directed downwards. Is that showing up? Not very well. I'm going to color it in black. That's not strictly speaking a free body diagram of the mass, right? But this is the upwards force of the spring on the mass, and this is the downwards force of this mass due to gravity. So the earth pulling down on that mass, and those two forces balance in equilibrium. So in equilibrium, we can see the force on the spring. Oops, that green isn't working well, let's avoid it. I'm going to call that K Y equilibrium. The spring force is a tricky one. There's a minus sign that people sometimes get confused on. In free body diagrams, we normally talk about K and Y equilibrium as this is a distance here. And this is positive constant. And this is a positive magnitude. And we account for the minus sign, the fact that it got stretched downwards, the force is upwards. We account for that minus sign with the direction in the arrowhead. So if I tried to be maybe a little bit more rigorous on this, I could say the force due to the spring as a vector is equal to K times the displacement of the spring as a vector with a minus sign. Now think about this. the displacement of the spring is downward, so delta y as a vector is negative. We want the spring force to be a positive or upwards vector, so this minus sign makes sense. However, in our free body diagrams, notice mg, g is not negative 9.8, it's a positive number. So here again, we see you've got a positive number, positive number. This is a magnitude, and the minus sign we account for with the arrowhead in an FBD. Again, positive number, we're assuming this is a magnitude with the direction being indicated by the arrow. In that sense, if we flip this all around, notice what we get here. In equilibrium, force of the spring, well, let's just write it like this. Ky equilibrium equals mg. So notice for this case, or in all cases, use FBD to determine the equilibrium position. So that's what this thing means. It's the equilibrium position. I should be careful. We just called it a distance. So you can see it's going to depend on, let me go through this one last time to make sure. Depending on if you're using a vector equation, you want to talk about a equilibrium displacement. We could talk about an equilibrium distance if we're talking about a force magnitude. So there's going to be a little bit of confusion on whether this y is a position, a distance, or displacement. In all these cases, we might want to clarify that when we're doing our work, whether we're meaning this is a position or a distance, just like I'm trying to do right now, maybe a bit poorly. I want to mention something else here. If I make the y unstretched equal to 0, if I make that position 0, and I call this the positive direction for this problem, let's see what happens with this delta y term right here. Am I going to have enough room? Yes, I am. So in this case, delta y becomes, we'll call it y final minus y un. And that's a sneaky thing, right? A lot of teachers start by teaching you a horizontal mass spring system. For those systems, the unstretched length is 0, and you oftentimes say, oh, it's just k times y. Really, it's the amount it's stretched. So it's y final minus y un. And in this case, because I'm using a vector equation here, I better slap on a j hat on here. All right. Now, what else did I want to say about that? Oh, amplitude, the last thing. So amplitude, we saw this thing oscillating back and forth, and you might have noticed it went about, let's see, this far. It was bouncing up and down beyond the equilibrium position, right? So it came to rest at the equilibrium position, but when it first started oscillating, it was bouncing up and down, back and forth here. This distance right here is not the amplitude, but it's twice the amplitude. So the amplitude is going to be letter A, and it's half of total oscillation distance. All right. So in this case, notice you could say this another way. It goes distance A above the equilibrium position, but it also goes distance A below the equilibrium position in this case, as it oscillates up and down. All right. And then I know this video is probably getting a bit long here. Let me show you one other thing. I've got a simulation here somewhere. Let me share this screen really quick. Let's go this one. All right. So here's, and let me show you these things in this case. I've got this mass oscillating. Let's show the displacement, right? Notice the displacement is from the unstretched position. Whoops. Right, the unstretched position is right there. When I snag this thing and put it on here and let go of it, it's going to start oscillating back and forth around the equilibrium position. Now look carefully here. Let me annotate something. Notice it's measuring things relative to this part of the spring. All right, so if I pause this thing for a second, oh, my annotations, where are they? There we go. Let me pause this thing for a second. Or actually, let's run it in slow motion. So when this thing gets to the bottom of the oscillation, where's my annotation here? All right, we're looking at this point again. And as we run this thing, we can watch as this thing oscillates up and down. We see that the position does go below the equilibrium line. Now, this gets a little bit annoying here because notice they're talking about the equilibrium of the mass, not the equilibrium of the equilibrium in this case is reference to the mass, whereas these dotted lines are reference to the spring. So just to show you that the equilibrium point really is in the middle, let's run this one more time. Let's erase all these. All right, let's run this thing. And then what I'm going to do is I'm going to add in, I'm going to slow this thing down. Okay, there we go. So now we are at equilibrium. And so what I want to show you here is this is the top of the spring at equilibrium. And if I run this thing here, right there, let's get rid of the mass equilibrium line. That's right there at the bottom. We could see, hopefully, if I annotate one more time, we see that, yes, this thing is splitting the oscillation in half about equilibrium. Again, the top of the spring is right here in equilibrium. Here's the top of the spring when it's unstretched, and here's the top of the spring at maximum stretch. So this thing really is oscillating about the equilibrium line, but this simulation is a little bit confusing when you first look at it. Okay, that's one thing I wanted to show you. One more thing to go. All right, let's show these forces. Whoops. And let's just go ahead and do the gravity and the spring force. Okay, when we're below equilibrium for the oscillation, we see that the net force is upwards, right? There's a net force upwards because the spring's been stretched so much that it overpowers gravity. As we run this thing, let's go ahead and watch this. Once we're above the equilibrium line, once we're above that red line, look at the net force. The net force is downwards. So below the equilibrium, the spring is stronger. Above the equilibrium, gravity is stronger. And again, what do I mean by equilibrium? This is the equilibrium location of the mass, but this simulation is talking about these dotted lines reference the top of the mass, not the center of the mass. All right, so I hope that makes sense. Let's stop the share right there. And I think there's one more thing I can mention. At the very beginning, we looked at this demonstration over here, and we saw that one of these masses oscillates at a different rate. So we see that this one with the larger mass, but with this different spring, is oscillating faster than this long spring with this little mass. So what factors are affecting that? Let me just write this on the board for you and see if it makes sense. I'm going to talk about it like this, and actually sometimes, let me see, I want to make sure. In my notes in the book, I'm going to use omega naught, and I believe, am I going to use F naught? I'm going to use F naught for these symbols. There's a reason for putting the subscript 0 on there. It has to do with resonance. We'll talk about it later, but I want to point out that omega naught, the resonant frequency of this spring, is equal to the square root of, I'll tell you, it's either going to be K over M or M over K, where K is the spring constant. Take a second, pause the video. Do you think it's going to be K over M or M over K? All right, here we go. It's K over M. Let's think about it. If you use a large mass, it's going to be hard to rotate, it's going to be harder to make a large mass change directions. You're going to require more force, more acceleration. Similarly, if you have a stiff spring, if you have a large spring constant, it's going to cause the mass to change direction quickly. So hopefully this makes sense. Omega naught is sort of like your RPM, not RPMs, but RPM. So the more stiffness you have, the more rapidly it oscillates. The less mass you have, the easier it is to oscillate rapidly. All right. And so if you want to, you can take a second and figure out how the period relates to that really quick. We've got an equation up here that relates frequency to period and frequency to angular. Pause the video, see if you can figure it out really quick. How does period relate to K and M? All right, I'm going to go. So it's 2 pi over omega naught, which is 2 pi times, let's see, what's that going to be? The square root of M over K. Think about it again. If you have a large mass, it's going to take more time to oscillate. If you have a weak spring, a small K, it's going to take more time to oscillate. All right, that's pretty good on that.